effect of temperature on resistance. For specific resistance, you know this relation, specific resistance rho, it's given by m over NE square tau. Tau, you know, is relaxation time. M is mass of electron, E is the charge of electron. So, basically, rho will depend on 1 upon n tau. We also know the relation R equal to rho L upon A. For the given length and area, we might say what is followed by rho, that will be followed by resistance also. So, here this is applicable for resistance also. That means we can say R will depend on N and it will depend on tau separately. The effect of temperature on resistance is mostly studied or talked about in terms of alpha. What is alpha? This is known as temperature resistance coefficient. Its unit is either per degree Celsius or per Kelvin. You see, degree is not used with Kelvin. One very important thing to be noticed over here is if you are writing for some, say, metal, that alpha is K per degree Celsius, then it's going to be the same value in per Kelvin also. And reason is simple, because here we are concerned with the temperature difference, and temperature difference will be equal on Celsius and Kelvin, both the scales. It is written as RT R0 1 plus alpha T. R0 is the resistance at 0 degree Celsius, RT that at T degree Celsius, and alpha I told you is known as resistance temperature coefficient. The change in resistance will be given by R0 alpha delta T. This is the method of finding the change in resistance when the increase or decrease in temperature is given. Now, we want to find the relation between three resistances having the values this way. Three temperatures are given and respective resistances are also given. In that case, you know, R2 minus R1 over R3 minus R1, this is going to be T2 minus T1 and T3 minus, it's not 2 in 1, this is going to be 3 in 1. Why? Because this same pattern will be followed by length also, followed by volume also, volume of gases, pressure of gases. So, this same pattern, when we study gas laws, there will write V2 minus V1 for volume, P2 minus P1 for pressure. This is applicable for resistance, pressure, volume and length also, length of wire or the rod. Then most common relation is used, that's given over here, T equal to RT minus R0 minus R100 minus over R100 minus R0, this whole thing multiplied by 100. This is most common format of formula being used for finding the temperature, because the resistances at 0 degree and that at 100 degree are most commonly given in the problem. You see, what is the rule of N? This we want to find. Here we have written rho equal to M upon NE square tau. For the metals, N is already so high that there is no effect of temperature. It's not going to change by increasing or decreasing the temperature. So, in metals, this is irrelevant while studying the effect of temperature. In metal, this counts a lot. In metals, we could consider this factor, dependence of rho on tau, and by studying the effect of temperature and tau, we can know what is going to happen with metals. In semiconductor, you see the number of free electrons per unit volume is not very high. And when we increase the temperature, covalent bonds that exist between the silicon germanium like semiconductors, that starts getting broken. And when the bonds are broken, number of free electrons available for conduction increases. N increases, that changes. So, rho will be affected by N for semiconductor. So, we will study these effects separately. Here one more thing is given. If there are more free electrons, that means more charge available for conduction, for current, obviously the conductivity will be higher, confirming that the resistivity is going to be lower as in the case of metals. Reverse is the case with semiconductor. And for as far as the temperature is concerned, it's given over here that because of change in tau, metals will have the effect on their resistances, and because of N, semiconductors will have the effect.